Okay. Hello. So my name is Anje, and I'm going to talk about the code review bottleneck. And since this is a lightning talk and we don't have much time, let's just dive right in. So to start off, we all know what code reviews are, right? It's basically our version of scrubbing in before surgery. So every time that we want to push the code to production, we want to make sure that that code is as clean as sanitized and free of bugs as possible. And to achieve that, we ask our peers, our co-workers, to review the code before it gets pushed to the users. So that's one important part of code reviews, but there's also, we also do them to share the knowledge between the team so that we have an opportunity to teach our co-workers about our code base and to learn from our co-workers as well. So it's a very important part in the development process. And we all also know what bottlenecks are. It's the part in our process that makes everything slow. One example is the neck of a bottle. That's where the bottleneck name comes from. And it's actually a good bottleneck because it helps us drink the water from the bottle without spilling the water into our faces. So there are good bottlenecks, but there are also bad bottlenecks. We all know, we've all seen bad bottlenecks in person throughout our lives. The most problematic ones are probably in traffic, where a lane closes and suddenly there's a big line of cars behind it trying to get past. So these kinds of bottlenecks is what we're trying to avoid, and this is what makes everything that we do really slow. So we're good at identifying bottlenecks in the real life, like in traffic, but for me personally, it was very hard to figure out how to identify bottlenecks in our development process. So how do I know if some part of our process is actually a bottleneck or not? And the answer to the question on how we can find bottlenecks in our process is just let's look at where things start piling up. In the slide here, there's a screenshot of the GitHub pull request page, and we can see that we have 6 pages of pull requests. So 50 pull requests per page times 6, it's around 300 pull requests open. That basically translates into 300 features that the users are waiting for, but they're all stuck in this long queue and not moving anywhere. So having a lot of pull requests opened and waiting isn't just a problem for our users because they're waiting for those features that aren't getting delivered, but it's also a problem for us developers. Because these pull requests sit there for a long time, we waste a lot of time just updating them, and to get back in. So after a week, when the pull request was opened, you sort of forget all the little details that you knew when you opened the pull request. So you kind of lose that context of that pull request quite quickly. And to get back, you have to delve into the code one more time and make sure that everything, you have to load back all that data into your working memory once again. The code that's in the pull request also gets out of date because there are other things getting merged. There might even be conflicts for you to solve, and that's all time wasted, and you're basically spinning your wheels and not doing anything productive for your users. The problem is that the solution for this particular bottleneck is not straightforward. You can't just come up with a weird machine that will make sure that the bottleneck does not exist anymore. You can't even buy a software as a service or a SaaS that will solve this problem for you. The only thing that you can do is to try to deal with the problem in a different way. For me, in my experience, the best way to deal with this is to change the way you think about your development process. So the main thing is that you should do everything as a team. Your goals, so your team, the development team, has only one goal, which is ship quality code to your users. And it might seem counterintuitive, but if you're just working on the tasks that you have in Jira one by one, you might be working against the goal of your team. So if you're working on the same issue, your same ticket for the last for 3 days, and if during that time there were 3 pull requests to review, so that kind of translates into 3 features for your users, but you were ignoring them because you were focused on your own ticket, you basically wasted 3 days of your team's through output. So in that time, your team could have shipped 3 new features for the users, which would make your users happy, and they would really appreciate it. So you have to sort of set yourself aside and focus on what's really important for your team. A few things that help with that is also the way that you write your pull requests and how you handle them. So your pull requests should all be as small as possible, and this might seem trivial, but it's actually really, really hard to do, because it means that sometimes you will have to split the code into multiple smaller chunks, and to do that you might have to add feature flag or some other type of flow control to make sure that nothing breaks. And then the next thing, you should always make your pull request reviews the top priority. So when we developers, we really like to be in flow, and we really hate it when our flow breaks. I say that there are only 2 reasons that are important enough for us to break that flow. The first one is if there's a fire in the building. In that case, you have to write a polite email to the fire brigade. And the second one is when a new pull request is opened and is ready for review. That's when you should jump on it and try to get it out the door as soon as possible. So as a team, this is going to be an iterative process, and you just have to keep improving and just try to figure out how to make things better as the time goes on. Now, at a few slides back, I said that there's no way that you can pay a SaaS company to solve this problem for you, or you can get a service that will help you solve this problem. I'm still convinced that you really can't, but that isn't stopping me for trying to write a SaaS service to help out at least a little bit. So I'm working on a little side project called codereview.chat, It's live now, but it's still not really working. But I'm happy to get some feedback. So the main purpose of this little service is to help you review code as fast as possible, basically by using real-time chat for your code reviews. So every time, the simplest possible implementation of this is when a new pull request is ready for review, a Slack channel is opened, the author and the reviewers are invited, and they can talk through chat or even hop on a video call if needed. And that's basically it. I'm open for questions, and if you want to contact me, talk to me about pull requests or anything else, these are my contact information, or you can just find me at the conference and I'll be happy to chat. Thank you. Any questions?
Yeah, so thanks for the presentation. I have a question regarding the pull request flow. You say that there are only two things, a fire happening or a pull request being open. Do you really follow that strictly? So you stop what you're doing and you go straight to pull request reviews? Or do you sort of batch that and wait for 2 or 3 to pile up, and then the next morning you read through the 3 of them and maybe take an hour, hour and a half, and like calmly do the review?
So I try to follow, in my team, we try to follow this as much as we can. Of course, if you're in the middle of something, you're not going to really drop everything. But definitely, we try to strive for the fact that pull requests should be reviewed in hours and not in days. And that helps a lot in the whole process.
Testing, testing. Yeah, so just connect it there. Displays. No, no audio. That's all right. Fuck it. Hello. Okay, so this is a quick lightning talk called TensorFlow Serving in Production. My name's Tom. I work for Onfido here in Lisbon. And we automate identity verification, which is quite a generic thing. We use a lot of machine learning for this. So can you show your hands? Does anyone here work in a company which uses machine learning? I know you do. Cool. Who here uses Kubernetes? Okay, so we use both of those. And this is how we, at the start of Onfido, this is how we deployed our models. So if you know Python, this is just a really basic Flask application. What it's trying to show you here is we have a Python application. We load the TensorFlow model using TensorFlow, and we just expose like a simple REST API called process, and we do something with the model, and we return the result. So nice and simple. It runs locally on your machine, and it works. But there's some downsides to this. It's pretty simple, but the models can get very large. So loading TensorFlow's models in Python adds a lot of overhead. So you just have like 25% just for the raw models like SciPy, TensorFlow, Scikit, all the crazy machine learning stuff that the researchers need to do. So it adds a huge amount of overhead. And that's not including the size of the actual models, which can get 200, 300 megabytes big. Flask is also single-threaded. So it's particularly bad because if you have a model that takes 5 seconds to sort of run, then you're blocked for 5 seconds. Nothing else can do that. The way that you get around this typically with Python is you have multiple processes. Simple. But multiple processes load the model multiple times, especially if you have multiple processes with multiple pods for redundancy. Basically, you end up loading this kind of 500 megabyte model just a whole bunch of times, and it costs a lot of money. I can't tell you how much we spend on AWS, but it's a lot of money, and I wish I had invented AWS. So the solution is TensorFlow Serving. Can you raise your hands if you know what that is, or if you've used it? Okay, it's going to be boring for you. So you run it, it's just an official TensorFlow project. So you can run it Docker run TensorFlow serving. Basically, it's written in C++. It directly uses TensorFlow, has a very low overhead, and all it does is take your models, as long as they're correctly annotated or set up correctly, it just creates a REST API for them. Simple. And the idea is you adapt your services to call these remote models. So it's just a REST API. So it's doing what we did before, but without Python. So an example, this is just from the sort of hello world. You would load your model. I don't know what this is. This is my model. You would post some JSON to it, so a bunch of floats, and you get back some more floats. This can be anything. This is just your high-tech startup or whatever, more machine learning things. There are huge cost savings with this. So this is a real-world example. One of our pretty cool applications. Before TensorFlow serving, it ran sort of 16 pods with 4 workers per pods. This is a kind of peak load. And it used about 60 gigabytes in production. We run a lot of models, so like this is just one part of the whole complicated pipeline that we have. But 60 gigs is quite a bit, and it's expensive. After TensorFlow serving, the whole thing could be served with 4 gigs of memory. Like it handled it easily. Unfortunately, my boss was like, yeah, it needs to be redundant, so it's 12 gigs. But it could just be 4 gigs. The point is, like, it's a beast. It really is. One of the cool features is it can transparently batch multiple inferences. So if you have like 10 different services calling the same model, all connects to the same TensorFlow serving instance or whatever at the same time, sends the same models, rather than doing 10 individual TensorFlow inferences, it will just do a single one, which potentially is faster, potentially it's not. But it's pretty cool. It can be optimized for your CPU architecture. So if you run TensorFlow locally, you get this annoying warning message, which is just like, oh, it's not optimized for your machine. The point is they distribute the compiled binary in like the lowest common denominator, so it runs everywhere. But if you're running it in production, it doesn't use things like AVX or some other instructions, which greatly improve the speed. Making the Python package do this is really annoying. I don't recommend it. You can bypass this and get GPU support by just using TensorFlow serving. It's all remote, it's all compiled for you. You don't need to worry about that in Python. The problem is it's written in C++. If you're a Python guy like me, that's not something you can easily adapt or fix, or if you need to do anything else, you can't add any logging to it, etc. It's kind of a black box. So the way we got around this is we had a small asynchronous Python service on a sidecar pod in Kubernetes, which basically means it runs next to the TensorFlow serving instance. That receives the actual requests. It adds about 20 megs overhead, and it just forwards the requests to TensorFlow serving. What this enables us to do is add stuff like Datadog monitoring, real-time stats, etc. in Python, because that's, for me, easier. And we get all of the same speed benefits of TensorFlow serving. The problem? Yeah, so model data sort of travels over the network. So it's kind of weird. Individual inferences are slower, but at scale, it's more efficient and pretty much the same. So you can get a lot more throughput by just sending the stuff over the network, even though individual ones are slower, if that makes sense. Another problem is it really wants you to do the googly way of doing things, which sounds really interesting. It really wants you to live reload the models. So I think at Google, where this was developed, they kind of have a much more complicated custom pipeline. If you're in Kubernetes, the whole point is the pods can go down and up, they're ephemeral, they're kind of isolated. TensorFlow serving likes to load these models from like S3, and it will poll for updates over and over again, which is not great, because if you push a broken model or something to an S3 bucket, boom, you've just disrupted production. Or if you remove them from S3 or something. They're not really atomic. So it's kind of, it does conflict slightly with how TensorFlow, with how Kubernetes wants to deploy things. But you can get around that by using some tricks like making the buckets immutable, so you can't like overwrite a model or someone messes up and deletes the bucket and suddenly production is broken. It's all kind of isolated in a single Kubernetes deployment. And another problem is it uncovers weird issues with your models. So in the one I talked about before, for some reason, the machine learning researcher who produced the model decided it was a good idea to take the image file, which is a compact binary representation of RGB values, transform it into a huge matrix of RGB values, and then pass it into the model, which I guess makes sense. But if you're passing it over the network, you have to serialize. You take this small, compact 100 kilobyte image, convert it into a ginormous JSON object, and then send it over the network. it's not particularly efficient. So it works locally, it's kind of fast, but when you add the network overhead, it slows it down. Another weird issue that we uncovered was it's a more strict to what it outputs. If you run stuff locally, Python uses 64-bit floats. If the model says it returns a 32-bit float, it does until you cast it to a float. And at that point, it's a 64-bit float, even though it's supposed to be a 32-bit one, if that makes sense. So with the model we had before, it would return truncated 32-bit floats, which turned out that's not what we were meant to return. It was meant to return 64-bit floats, which caused some issues with our accuracy. That's pretty much it. We're hiring, by the way, if you want to come help me with TensorFlow serving. And do you have any questions? I don't know how long that took. Probably wasn't 10 minutes. No questions? Everyone's super clear? OK, go use it. Go on, Daniel.
My name is Gil, or Gil, if you're Portuguese. How to write a book with code. So I have no slides. This is just so you know what I'm talking about. So who here knows about NaNoWriMo? Okay, so NaNoWriMo is National Novel Writing Month, which is a few people in the month of November. They get together, each in their own homes. That would be weird. So, and they commit to write a book with 50,000 words in the month of November. But that's boring for me because I'm a developer. I don't like writing. I like writing code. So there's the NaNoGenMo, which is National Novel Generational Month, which is to do the same thing. You have to write a book with 50,000 words, but you write code that writes that for you. So that's much better. That's lazy, developer style, right? So I'll take you back. Close your eyes and let's go back to 2018. Yeah, that was last year. In the month of November, I committed to do that. So I've always wanted to do generational stuff, like generational art, generational anything. So I committed myself to do that for the month of November. And I had an idea. Who here loves Dungeons and Dragons? Wow. Well, I love it a lot. So if you don't love it, I can tell you how it looks like. It looks like a dungeon, right? Adventurers go to a dungeon and they kill monsters, they kill well, you remember what it was there, right? So you kill monsters, you get treasures, you get loot, and basically, it's cool. So I wanted to write a book where you could see like adventurers going on a dungeon and doing cool stuff, like killing orcs, getting treasure, eating food. So what I did was I wrote a Python app, which was just prints all over the place, randomness, and it would just randomly create adventurers, orcs, dwarves, all the normal races in Dungeons and Dragons, right? I created my own combat system because it was much simpler. I just had 1 month to write the book, right? And then I was just like, it was just one corridor because I didn't want to like get directions for people. So I just wanted them to go straight through, kill one orc, get a pizza, kill another orc, get a treasure. In the end of the, if they got to the end, they would stay there. We would shuffle the corridor and we would get another adventure to go through, kill everyone, and just like randomly. So on a loop until I got the 50,000 words. I mean, I did like fingers in the air, and the book ended up with 1,500 pages, so that's fine. In the end, you got like an annex for like to geek out on the weapons. Like each weapon had a list of the enemies that they killed. And you could see like, this is the coolest weapon, the iron halberd, or whatever the best weapon was. So, I mean, the code was so awful. The code was just like, no TDD, don't look at the code, please. But it was fun. Like, I got home every day after work, and I had like lots of ideas, and I would just like write them up, and I mean, it felt great. So, I mean, I haven't told you how to write a book with code, right? And that's because I lied to you. This talk is not about how to write a book with code. This talk is about committing to do the thing you've always wanted to do for a month. So now is your turn. When are you going to do that? Thank you.
Hi, so my name is Daniel Serrano. I'm a software developer at Onfido. So Tom's colleague, yeah, have to put up with him every day. He's on my team. Imagine that. So I'm here to talk to you about native code in Elixir. But first, to get into that, we first need to know what Elixir is. So for those of you who don't know, and I see a lot of people from TalkDesk, so you guys all know what Elixir is. Elixir is a dynamic, immutable functional programming language. It sits on top of the BEAM, and it leverages that, so the Erlang virtual machine, to give you a fault-tolerant environment in which you have very low latency. It's very much a distributed environment, and it allows you to also use the actor model like you would do with Akka if you're coming from Scala. And this actor model encompasses a series of processes that are lightweight processes, so not a mapping. There's no direct mapping to operating system processes. And basically, they're very lightweight, and they have their own BEAM abstraction that you can use. So what is a foreign function interface? A very complicated name to just say that you have a mechanism, generally in programming, to interoperate a program written in language X, have it communicate with a program written in language Y. So calling C code from Elixir is possible through a various number of ways, like ports, port drivers, C nodes, JInterface, or NIFs, and I'm going to focus in this talk on NIFs, so native interface functions. Why did I do this, by the way? I don't think there's a slide for that. It's just because I wanted to play with FFmpeg. The hello world for using NIFs is here. You have to use the Erl NIF C library. It gives you API functions to do your own Erlang NIF library. In this case, so on the top right, you can see the Elixir code. It's very simple. You just have to use the onload callback in the module to call the Erlang function to load a NIF. This would be your compiled C library. In this case, helloworld.so. You don't see the SO there. That's omitted. And then you define the name of the function that you want to import from the C land into Elixir. You raise an error in case something goes wrong with loading it, or you're simply misidentifying the function. In the C side, you have a very simple callback to each function that you want to call from the C side. It has always 3 arguments. The first one is the environment, which tells you a series of environment configurations of the Erlang virtual machine in which you're running that program. argc tells you, obviously, the number of arguments that function has in Elixir, and argv has a series of marshaled objects that represent the terms in Erlang. In this case, it's very simple. All I want to do is just return from C a string that can be represented and marshaled back into the BEAM. So I use the inif make string function that comes out of the box with erlnif. So FFmpeg, I'm sure most of you have used it in your lives and probably at work. It's a library for manipulating video and also doing some bits with audio. It comes with FFmpeg, a binary for FFmpeg, also FFprobe. They both use libav codec underneath, and yeah, you guessed it, it's a C library. So we can we can potentially, instead of like have your program shell out to call FFmpeg or FFprobe, you can actually call that directly, and it would be much less expensive. So I actually benchmarked this with Benchy, a benchmarking library in Elixir, and just to fetch the duration of a video, it's up to 10 times faster. So you can like think about extracting audio, single image from video. These are various examples from a gist I found online. You can do all sorts of things with FFmpeg. It's really powerful. For this case, in specific, I just wanted to take out the format of the video. So if it's like a MOV, it will say QuickTime, MOV, Apple Video something. If it's MP4, it will just say MP4 and whatnot. So here it's very basic. All you have to do on the C side, which is a really hard part, as you saw before, is in this case you have to allocate enough space to get the file name that you want to inspect. Just create like a bunch of null terminator characters for the string. Then you copy that according to the size of the string that you just got from the Erlang side. You alloc an FFmpeg AV format context, open it, and it's just a matter of filling up a map and pass it on to the Erlang side. In this case, I'm using the inif make new map function to create a new map from the C land into the BEAM side. I then create two strings, one for the key, one for the value, one for format. So basically, in this toy example, you'll have like a hash map with the key being format and the value being, I don't know, like QuickTime or MP4. And then you put that key with that value into the same file, into the same file info variable, which was the map. This is really cool and dandy, but NIFs have two major problems. One of them is slowing down the BEAM. So the BEAM, the Erlang virtual machine, uses this concept of reductions to make it to handle its preemptive scheduling. So like imagine a function is taking too long, it assigns it 2,000 reductions by default to each function. And it's like, okay, you can run like 2,000 reductions and then I will preempt the hell out of you and like call some other stuff. In this case, with NIFs, you don't have that concept of reductions on the C side, because like it simply doesn't exist, right? It's not the BEAM. So you have to be sort of judicious of this, and the Erlang team advises you to keep things under 1 millisecond. If you can't, you can use something like yielding NIFs or threaded NIFs to sort of give some hints to the Erlang virtual machine of how many reductions have passed. You can do this in terms of percentage and whatnot. You can read more about it on the ErlNIF library, but the really cool one is dirty schedulers. In a library like FFmpeg, you don't have control over the source code, so you can't go into it and start to modify it to like middle way, be like, okay, it's like sort of like 3,000 reductions now and sort of like 6,000 now. You can't do that because it's like, it's a binary usually, you don't have control over it, or even if it's a library, you don't want to mess with it. So what you can do is use the concept of dirty schedulers. I'm just going to deny this, Tom. Hope that's fine. Because Tom is lending me his laptop. Long story. Yeah, so in the dirty schedulers, using dirty schedulers, sorry, you can actually instead of using the sort of simple quote-unquote schedulers from Erlang that run your code, you can run two additional types of schedulers, the IO-bound schedulers and the CPU-bound schedulers, and you can run your program in one of those. And in that way, the BEAM, we sort of have an extra level of interaction to yield your code in between the preemptiveness that it can't reason about in the C land. You can also segfault the BEAM, which is a real bummer. So NIFs are executed as a direct extension of the native code. If you have a segfault in your code, you will crash the VM and your entire life will come crumbling down. Processes, state that come with it, it will all be vanished. A good alternative to this is using something like Rust, and there's a really cool Erlang library that I haven't used myself, but it's out there and it seems really awesome, which is rusterl. With all the memory safety guarantees and data race free threading of Rust, it seems like a really good contender to sort of avoid this second issue. But again, it's not a silver bullet. I just want to say one last thing about segfaulting BEAM, which is if you're using something that's like battle tested like FFmpeg is, you already have in the C code itself a lot of safeguards to this, and I could see that in play when I was doing this toy example. If you have any questions, I'm here to answer them. Not all of them because I'm not an expert in C, but throw them away and I can see what I can do. I have a blog post written about this, so if you want, you can check it out in dnlserrano.dev. Yeah, I think that's pretty much it. Thank you. What are?
Hi. What are reductions? Reductions.
So, good question. So, reductions is that sort of like, I think it was Sasha actually from Talkless that used the expression, it's the cash money of the BEAM. So it's basically just the way that the BEAM has to. So the BEAM is a preemptive virtual machine. It's executing code, and then it's like, okay, you stop executing. I'm going to execute something else, and then I'll get back to you. And so it hands 2,000 reductions to each function that you have, and so it. Basically, if something is taking much longer, doing much more operations than it is permitted, it will just count that sort of like how much effort that's bringing into the processing of your program, and be like, okay, you've done enough because you've spent all your reductions. Now I'm gonna do some other stuff, and when that other stuff spends all of its reductions, it will keep yielding and yielding, and that's what gives this preemptiveness of the BEAM and all the sort of scaling capabilities and whatnot, because it's really judicious of its time and its spending.
Daniela, thanks for your talk. You mentioned the possible alternative approach based on Rust to avoid, segfaulting and things, but there's no silver bullets. If you're targeting using a library like the FFmpeg set, you may as well wrap it in all the Rust in the world because you will not be safe from C's problems. Or is there some magic wand that I'm not aware of?
No, yeah. So sure, that's nice observation. Maybe I should have been clearer. So when I was talking about Rust being a good alternative, it's not for the case where you want to use FFmpeg. It's when you're thinking about doing some like performance-heavy code, like I don't know, one very well-known and very common is cryptographic libraries and whatnot. You can use Rust instead of using C directly. But yeah. No silver bullet at all. Like when you're using FFmpeg, just know that if you're using a good enough battle-tested C library, you probably won't get into a lot of these problems, but beware that you can. And if you're running like 3 pods of your service in production and one of them goes down, maybe 2 will not be enough to take your load. So like be extra judicious when you start putting these things on top. But yeah, definitely not a silver bullet. Okay, no more questions? Thanks, guys.
So we have 15 minutes left, so if you have anything you want to show us, now it's the time, until the 8 p.m. Otherwise, the lighting also just finished.